Okay, so hi, I'm JT. I'm currently at Monkey, but sort of my background is I was undergrad at the University of Minnesota and did like an honors thesis on machine learning. I went to the University of Utah, and then they're sort of focused on programming languages. But concurrently, I've worked at Mozy, Google, Instructure. And have had a wide variety of focus, but most of the time my sort of professional work has been with distributed systems. So that's sort of, and I never updated the title. This has nothing to do with Go. I gave a previous version of this talk, sort of, the previous iteration was at a Go meetup, but anyway. Okay, so as far as like sort of speaking style or anything like that goes, constantly am interrupting myself, so you guys should feel free to, because it makes no difference to me. So if you have a question or something, just like please just let's just address it and keep going, because I mean I know I'll forget, and if it's relevant, let's dig into it. And then the other thing is I think I have 145 slides. They're all transitions. So yeah, no, they're all of them. No, I'm just kidding. I do have 145 slides though, and there's a lot of sort of high-level detail, but I'd like to dig into the areas that you guys are most interested in. So, totally lost it.
So you're gonna dig down on the...
Yes. Okay. So I have a ton of slides, and I wanna sort of like. I can talk about stuff at a high level, or we can like sort of dig into something. So if you have questions, or if you want to go into a little bit more detail about a particular topic, let's do it. This does have some of my slides from the Go talk, and so some of the more introductory slides I'm going to sort of skip through. So stop me if you want them. Does that make sense? Okay. Okay, so what is computing and why? Basically, distributed computing, just at a high level, is multiple systems that are communicating with each other to sort of achieve a common goal. With there's no global clock, components are concurrent, and there's independent failure of components. Okay, so why would you want this? Fault tolerance and horizontal scaling are really the two main reasons. Okay, so why is it hard? There's a number of different reasons, but as sort of the list of ones that I've had a lot of issues with, when you build a distributed computing system, you end up putting in a lot of fault tolerance, and sometimes that can mask failures. So it's actually like to have, if you end up having a distributed system and someone comes to you and says, you know, it's kind of slow, that's like the hardest problem to solve, because it may be the case that it's slow because you suck. It also could be the case that it's slow because it's actually working as advertised and some failure got hidden. So fault tolerance is actually sort of, you know, makes it hard to find. Distributed computing is hard because, you know, sort of as you have more systems, the more complexity there is. And then you have to worry about security between the systems, because if they're, you know, especially if they're operating in a Byzantine environment where the systems are not in your control, which is currently the case with Space Monkey, and with the NSA revelations is the case with everyone else. You know, you need to worry about it. Okay, yeah. Okay, some security problems. So failures are a huge problem with distributed systems, and you're not going to avoid them. So I made this graph. This is my LaTeX skills. I made this in LaTeX. This is the probability that you will have a failure given a number of components. And if your failure rate is 0.01%, 1%, sorry. If your probability of failure is 0.01 and you have 400 components, you have like almost a sure, like you're going to have a failure. So, you know, multiply this by time. If you have a 5-year mean time between failures for a hard drive and a 0.05% daily failure probability, and you have 10,000 hard drives, 5 drives fail every day. So failure is just going to happen to you if you're building a large distributed system, and there's just nothing you can do about it. So, you know, there's various levels of this, right? Like, okay, the easy thing is your server crashes. A little bit more complicated is like a router drops and 2 servers can see each other, but they can't see a third server in the same way. We've actually seen at Space Monkey, everything working except for a specific TCP stream has dropped. So a router or some home device will actually be routing everything but the TCP stream you care about. You can get RAM corruption, and then of course there's adversaries if you're working in a untrusted environment. Okay, so another really big complication with distributed computing is latency. When you have a system that's connected to the internet, you have some links, and it has poor throughput. When you have throughput, you can improve it by adding multiple links in parallel. You can increase the bandwidth of the system by core links together. But if you have bad latency, there's nothing you can do. Your latency will be there's just no way to improve the speed of time of there's no way to improve how long it takes for your light protons to get from here to France and back if your system depends on getting from here to France and back. So if you have latency, there's just nothing you can do. So you want to minimize it. Okay, so there's this quote. Basically, in the last 11 years, oh yeah, bandwidth increased 1,400 times in the last 11 years, but latency has only improved like by 10 times. So, okay, so yeah, so basically with Longtails, if you have a bunch of systems, if you have a number of components, I made this in LaTeX. This graph. If you have a number of components and you have and you're worried about having, each component has a certain amount of variability where it might end up having some sort of latency spike if it takes too long. Like maybe there's a garbage collection pause in your system, or maybe like the hard drive is busy doing something else. If there's a variability in latency, the number of components, you're going to have high latency events. So you have to worry, like if you're waiting for 12 systems to return to you, you have just increased your chance of having to wait. One of those systems is just going to take forever, or 100 systems or 1,000 systems. The more systems you wait for with a long tail, the more sure you're going to be that it's going to just take forever, regardless of how fast they all are. So, I think this was Sun Microsystems came up with a list of fallacies of distributed computing. These are all fallacies. The network is reliable, latency is 0, bandwidth is infinite, the network is secure, topology doesn't change, there's only one administrator, transport cost is 0, the network is homogeneous. And those, none of those are true. So, wait, that's laws of nature. Oh, here's another sort of complicated scenario. So let's say you're trying to build a system where you want, so this is the two generals problem. And you have, and if each one of them, if A1 or A2 attacks town B by themselves, they'll get destroyed. So they want to coordinate together. They agree that they're going to attack, but they haven't agreed what time to attack. So they have to figure out, through sending messengers through this valley that B controls, who are going to attack. Let's attack at 4. The trouble is, if A1 is the only one to attack, if the messenger is kidnapped or something, and A1 is the only one to attack, then it's going to be.
And since we're not redundant, A2 can't make up for the lack of A1, therefore the whole A side is going to lose.
Yeah, well, eventually, it depends on the probability of failure for the messenger. Right, so you can add acknowledgements, right? So you can try and fix this problem with adding acknowledgements so you send a message to A2 and A2 is going to reply and say, got it. But the trouble is, what if A1 doesn't get that message? Should A2 attack? If A1 doesn't get the acknowledgement, then A1's not going to attack, so should A2 attack? So you should add an acknowledgement for the acknowledgement, right? No. This is just a complicated sort of law of how this sort of system works, is that, in general, because links are unreliable, you have to deal with things sort of more stochastically. Anyway, so this is a common problem with trying to agree and come to consensus with something. Okay, so let's talk about consensus. So the definition of consensus is nodes achieve consensus when every process that's correct agrees on the same value, that every correct process decides at most one value, and the value that it decided has to have been proposed in the system. All of the processes have to eventually reach a decision, and if all the correct processes propose the same value, all correct processes decide that value. So that's a group of processes coming to consensus. Okay, and in the theorem, the FLP impossibility theorem, is that in an asynchronous environment subject to failure, there does not exist a deterministic consensus algorithm, even if messages can never be lost, at most one process can fail, and it can only fail by halting. So even in the scenario where you're super lucky and you have these three properties, you still cannot build a deterministic consensus algorithm. So that's just like a proof. Okay, so there's the CAP theorem. Maybe I should point out at this point. So I'm working on setting up a distributed systems meetup and reading group that will meet bi-monthly. I mean, every other month. English is where sort of my expectation is we'll pick a paper and actually go into these proofs. We'll go into sort of things like this if you have interest in that, or if you just want to learn about other stuff that's distributed system-wise. So meetup thing that I'll send you guys all a link to over Meetup. But anyway, so if you want to talk about this proof, we can talk about that in more detail. Okay. The CAP theorem is a commonly, people talk about the CAP theorem when talking about distributed. And the theorem is basically the sort of the common way of understanding it is choose two of three between consistency, availability, and partition tolerance. At the same time, availability is a guarantee that every request receives at least a partial response, and that's not just like error. Like error doesn't count as a partial response. And partition tolerance, the system continues to operate despite arbitrary message loss. So typically people talk about the CAP theorem and say, great, choose two of three, but the truth is, okay, so actually I'll get to that. This is sort of a Venn diagram of all the sort of possible protocols. Consistency and availability in the middle is two-phase commit. Consistency and partition tolerance is Paxos. Partition tolerance and availability is gossip, and I'll talk a little bit about these things. But the truth is, you can't skip choosing partition tolerance. Like, the fundamental facts of computing hardware is partitions will happen. So you can't skip that one. So what that really means is you get to pick consistency or availability in a system. So you can't have both.
So how do big players like Google give the appearance that they're meeting all of it?
Sometimes they cheat. But yeah, so I'll get to that in a minute.
Okay.
I'll get to that in a minute. Okay. So just to talk about if you need to solve one of these problems and this is just sort of a side note, if you want to solve one of these problems and you're like some brand new company and you haven't built anything yet, there aren't really many out of the box solutions because large entrenched players don't really have a lot of incentive for like releasing their stuff. This is sort of improving now with like Zookeeper and like some of these Hadoop HFS projects. But for the most part, people who are contributing and volunteering their time to an open source project don't have the resources to test these things at scale. So it's not really the case that there's high quality open source, out of the box solutions for these problems that fit your use case, like there are for a lot of other non-distributed things. Okay, so then I'm going to talk about some ways of coping, and I have a lot more detail here than in the previous iteration of this talk. Okay. So in the previous version of this talk, I said service-oriented architecture, and Ben pointed out that there are a few different arguments about whether or not a monolithic application is beneficial compared to having a bunch of little REST services that all talk to each other over HTTP, and that's not really what matters here. What matters is making sure that you can argue about whether or not you use REST to break apart your system, but really what you do is you need to small modular components to sort of understand and make sense of all this stuff. And they're all in the same process. It's just a matter of making sure you have concise interfaces between all of your systems. I'll talk about Paxos and Raft in a minute, but that's the main reason why Raft is so much better than Paxos, is because they sat down and came up with small modular definitions of their protocol, and Paxos is a nightmare. Okay, so, and if you do have sort of a service-oriented architecture, you can establish SLAs better and a lot of other things. So if you're going to build a distributed system, try and figure out sort of the smallest component that'll actually work and is understandable, and use that. Go ahead.
I would argue that the distributed system nature just makes things harder in general, and so it forces you to follow good practices that you should be doing anyway.
Yes, I would agree with that. I would agree with that. Okay, so that's just what I said. Okay, so let's talk about thundering herds for a minute. So basically, what can happen is if you have a bunch of systems and processes all working together, every time two processes will coordinate on some task, they sort of get locked into a step, like, synchronous steps with time, as far as, they both just came to an agreement over here, and now they're both going to go do something else. So every time that happens, a little bit of entropy is taken out of the system, and what that can mean is you can just kill stuff with a thundering herd effect. And so, like, an example of that is if you have a bunch of processes all waiting for some cache key, and they're all constantly hitting a cache key, and the cache key is protecting some really expensive database query, and your cache key then expires, then all of a sudden all of the requests that are hitting that cache key now all hit the database, and the database falls over. Another example is AdBlock Plus. They used to have updates listed, and they would go and check for updates every 5 days. And what would happen is people's computers would be off in the office during the weekend. And so after a while, all of the computers started getting on this Monday update. They would all updating. Block started noticing is because all of their programs were updating on Monday every 5 days, getting their update server just swamped with requests on Monday. So you get these herd problems, properly re-add entropy back into your system. So a good way of doing that is called jitter. And jitter is typically bad when you're talking about, kernel scheduling. But in the case of distributed systems, you really want to, every time you have a timeout or a delay, two good ways of doing this. You can have all of your systems have different distinct prime number intervals, and that way they'll never each other and line up. Or distribution. So if you have some amount of like, say this is like a 24-hour time span. If you were going to try and have a bunch of events sort of randomly, uniformly distributed across this time span, if you want them to be uniform, the distribution for the interval in between random points here is called an exponential distribution. So if you randomly pick sleep times from an exponential distribution, the interval between all of your events will actually end up looking uniformly distributed across the day. So that's another good way of sort of, if you add an exponential distribution amount of variability to all of your sleeps or timeouts or delays, then it's much harder to get thundering herds because you're continuing to add entropy back into your system. And another, I'll get to this. I hope to talk a little bit about Raft, but Raft is really good at this. In fact, they use that as part of their protocol. So, okay. So the power of two choices. This is another great design strategy, and this is a really cool observation. So, when you're load balancing, one thing that you can do when you're load balancing is, like, you can just randomly pick a server, right? And the thing about randomly picking a server is that's kind of not so great because you're not actually making use of any of the information about how loaded your servers are or what sort of the queue is. But depending on sort of your system, it can actually be worse to try and pick the server that's least loaded. So if you have some sort of indication of load, and your load balancing algorithm is trying to just pick whatever server has the least amount of load, what'll happen is if you have a bunch of clients all doing this, and there's a little bit of delay in the notification of how loaded the servers are, they'll all swamp the one that's least loaded, and suddenly it'll be the most loaded. And so you start getting this really weird sort of effect of things falling over. So the power of two choices is basically this is a sort of a strategy for dealing with all different things, from hashing to cache coherency and load balancing and a bunch of things. But basically what you do is you randomly pick which one is less loaded, and then you pick that one. So this photo came from a blog I found. This guy ran a simulation, and it took 8 per request per server for the request to be pulled out of the server process serially, sequentially. So we picked which server to go to in queue time, and this cache load. So the cache load refresh interval here is how frequently the client found out new load information from the servers. So the immediate accurate, picking the lowest, picking just the best server to distribute to is great because you actually have immediate up-to-date information. But that's typically not the case. It gets really bad out there, and this is what I was talking about how the worst. You can have the scenario where you have a bunch of nodes or a bunch of clients, and they all end up piling on the guy who's the least loaded and ends up becoming the most loaded. So best of two is the red guy, and this one sort of seems to have sort of the best overall behavior. Best of three starts getting a little bit of the best effect. But best of two is much better than random when you have sort of low amount of time between finding out load information. Does this make sense? Is everyone tracking? Okay. Any questions on that?
What is the cache load refresh interval do?
This is just it's how frequently the clients find out new information about how loaded the servers are. Yeah.
That's a round robin date.
Huh?
Round robin.
Round robin is essentially the same as random pick. I think if he, I mean, I don't think he plotted that here, but I think if he was going to, it'd be indistinguishable from the blue one. Okay. Okay, so let's talk a little bit about shallow queues. So have you guys heard of buffer bloat? So buffer bloat is a problem where what's going on with TCP, if you know TCP, TCP's congestion control algorithm is based on actually how many packets drop. So as you're sending, so TCP is sending packets and getting back acknowledgements and going back and forth. And the way that TCP is able to figure out how quickly it can send data through is how many packets drop. And so what's happened over the years is as memory has gotten cheaper and it's been more and more cost effective to just throw the little routers and things, all in between hops between you and whatever server you're talking to have been getting more and more RAM. And what that means is their queue of possible packets have been getting dropping the rate that they use. So the TCP cannot react as quickly as they possibly could if those queues were really small. So TCP would work like your web things. From my experience, C problems haven't really changed much in the last 10 years, and some of that is just hard to fix, but a lot is due to buffer bloat, where what'll has a huge queue of outgoing packets that my packet can't get out because all your packets in the queue in the way. And so TCP will start doing this thing where it'll dumping packets, and then the queues get filled, and then it doesn't know how to back off because it doesn't have the feedback mechanism of the packets are getting dropped. So buffer bloat is an example of why you should keep your queues shallow. This is sort of a common problem. Anywhere that you have a queue, if you have some sort of high-level policy that you want to take effect, it won't take effect very quickly if your low-level elements have big queues, because they won't be able to react very quick. Does that make sense? So Yeah, if you have a queue, keep it really small unless you have a very explicit policy that you want to manage on top of that queue. If you keep your queue small, it also allows you, so I have a list of like further reading at the end. And there's this great ACM paper by Jeff Dean and I forget the other guy's name, from Google, and they talk about a lot of the lessons that they learned building large systems, and they talk about how there's very different workloads at Google. There's workloads where you have sort of slow background jobs that are just sort of constantly running, and then immediate jobs that are like the user requested this, needs a response. And if you keep your queues really big, it's really hard for that fast request to jump in and do its work when there's a bunch of slow, like long background jobs in the way. So they actually don't use the disk scheduler in the kernel very much. They actually try and do their own disk scheduling at a higher level to try and keep all the disk queues small.
Related to priority queues, take care of some of that.
Priority queues help for sure, but really the best thing to do is to build your policy at as high of a level as you can. If you end up having really small queue, regardless of your queue size, another problem is head of line blocking, and that's just sort of something that you need to worry about if you're queuing stuff. If you have some job and it just takes forever because of variability of latency, you want to make sure that your jobs are sort of broken up small so other things can get ahead. Anyway, okay, so other sort of general advice before I start getting into some algorithms and stuff. Oh my god, so initially I built this system at Mosey that was a replicated SQLite database. For every user got their own SQLite database, so it was massively 80,000 users, and for each user we had a SQLite database. It was replicated across 4 machines, and so we were doing this thing where we would apply edits to the SQLite database, and then we'd apply to the replicas, and then we change which one was the master and whatever, and then master and then was behind. We'd actually replay the log to the new one, and I didn't put back pressure into it. And so back pressure is basically if imagine you have a bucket and you've got a hose, and you just turn the hose on and you don't care about how full the bucket's getting or anything like that. Like, back pressure is basically saying, I want to control the rate of input based on the rate of output. So like I want to say, hey, wait a minute, don't send me another request until I've responded to the first one. So you want to actually sort of make sure that the server that you're talking to is keeping up with the request you're giving it, because if you start giving it more and not waiting to see if it actually is done with the jobs you gave it, you'll just kill it. So on that same story, what happened was, So on that same story, this system that I built, like we started scaling it up and it was looking good and everything was looking happy, and so we actually tried a little failure and it worked okay, and that was great. And so then we started adding more and more users to it, and we got to the point where we had added enough users to it. We're like, yeah, and then a failure happened, and it wasn't planned. And what happened was the recovery system of sending the replica log back to all the replicas took a significant amount more resources. And so what would happen is the server would come up, because it had just finished failing, it'd come up and all of the other nodes would start sending it their replica logs, and they wouldn't wait to see if it was like processing them at a good speed. And so they would just slam it, and then it would go down. And so these servers are now constantly sending replica logs. And what happened is there wasn't enough memory or network bandwidth available for those servers because we hadn't adequately planned for recovery capacity. And so they started to go down. And so that was a really fun weekend. Yeah. Another good lesson is you definitely want to put headers on it. If you don't have a way of being able to have your data at rest before it's compatible with some possible change down, it's so frustrating. Like, if you have a place and you're like, maybe I should put a header on it. Header everywhere. Okay.
Like a little thing.
Just like a little metadata. This is version 3 of the object and it obeys properties. Yeah. So I was talking about latency and long tails. When you have the large system, probably has the key that you're looking for, but it might not. To wait, actually find out if that system hasn't just lost it, you actually have to wait for responses from everybody. You can do really fast requests looking, because if this, you can just take the first response. So you get the best of the distributed system. The fastest node that returns is the response you get. But if you're doing a negative acknowledgement, if you're waiting for a key that's missing, you have to exhaust your entire possibility space of where that key might be, and that's going to mean waiting for the worst of all of your performing servers. So if you can design a system to just try and avoid negative acknowledgement, like, is this key missing? Like, you'll be much happier from a distributed system design perspective. You can use Bloom filters. So this is what LevelDB does. What?
Just the phrasing of negative acknowledgement there. You remember to phrase it as a negative response to query. Acknowledgement to me seems like, oh, I got your response. I'm acknowledging you. And in that case, in a widely distributed system, you do want to use negative rather than positive acknowledgements.
That's true.
Because
my wording is probably,
my head is in
this is
protocol space.
Yeah. Okay. Good call.
What's a Bloom filter?
So a Bloom filter. So a Bloom filter is basically a data structure where it can respond to a query in one of two ways. It can either respond no, or maybe. What? Yeah.
It's maybe or definitely not.
Right. Maybe or definitely not. Right. And the way this works is you have some hash or some large chunk of memory, and you have a number of different hash functions. And what you do is when you put an item into the Bloom filter, you put you hash that object and put like a little marker in a bunch of different spots that are sort of a unique fingerprint for that value. And if you check that tree or that object, and later you're looking to see if this object was ever in there, and one of those values is missing, you know that no one put it in there. If an object and it exists, it could be the case that a bunch of other objects all bits. And so that means that if you check for an object and it does look like the Bloom filter has it, all you can say is maybe. So a way of having a no or maybe for a much larger data set than might fit in memory. And so Bloom filters really help with what I was calling negative acknowledgement. And this is what LevelDB does. Key value store that Chrome uses. There's been a number of different forks. The Hyper people have HyperLevelDB. Facebook has RocksDB. There's a bunch of different implementations of it, but basically it's this system where you can do fast key value storage, and it's a log structured tree. And it does negative acknowledgement with Bloom filters. This is another sort of just Mosey lesson. If you have like a database or something, don't let multiple services talk to it. Like, you should just have one service talk to the database, and then all the other services should use an API, because otherwise you can't ever change the schema. Another just sort of small lesson is you should use deadlines and timeouts everywhere because of this long latency problem. You'll be like, this request will never take more than a second. And wow, we have a stat on a file taking 3 minutes. Like, I've timed it on some of our customers' nodes. Like, they're in situations where the disk controller is swamped, and this stat on this file took 3 minutes to do. Like, whoa! So if you have if you have any sort of expectation about how long a request is going to take, you're wrong. And you should put in like some timeouts and deadlines to make sure that you are close, or at least your service does something reasonable if it takes too long. So this here is people tend to try and make sense of all of this data that they might be getting from a distributed system with averages, and averages don't tell you anything about your distribution. And in general, a lot of things are normally distributed, but probably not any of the distributions you're looking at. Most of the distributions that are like failure distributions or any sort of thing to do with a distributed system ends up being an exponential distribution or a Poisson distribution or something else. It's not normal. And so if you have an average and you're just adding up all the things and dividing by the amount, you have the mean of a normal distribution, but that doesn't really help you because you might actually have a completely different distribution. So if you use percentiles, if you keep track of the 50th percentile, which is the median, the 90th percentile, the 99th percentile, what that gives you is a much more accurate, okay, 99% of requests all finish underneath this amount of time, but the last hours for some reason, like but the average would tell you that. The average is going to be, and then clocks are always wrong. Just always, they're always all wrong, unless you're Google. So we'll just have a quick true time. So you guys, the Spanner paper, they released a large distributed SQL-style database. They've released a globally relational database that's consistent. It's equal, like it's actually like a relational database, and it spans. And the they got so most of these consensus protocols, and I'm going to talk about some of them, lots of complicated things to sort of agreement about where things are, because everybody has a different idea of what the time is. And so what Google Spanner does is they actually put in each data center, they put atomic clocks and they put GPS clocks and they put all of these different clocks for hardware in their data centers. And then they got a bunch of like really complicated systems to measure the possible error for those time systems. And they figured out the exact range of error for the GPS clock and the atomic clock. And then they figured out how much that error drifted over time. And then they wrote a library that uses this so that you can say, what's the current true time is what they call it, and it gives you back a range. All you know is that the time is definitely within this range. And because they can use that, they can know that all of the computers across their global network have the same range. Like once the range has passed, that event is over for sure across everything. And so what that means is they actually built their system to actually rely on time and to keep track of all sorts of things without having to worry about acknowledgement and all sorts of. So anyway, I'll hopefully get to some of that. Okay, so let's talk about some algorithms here. So this is a useful algorithm for dealing with disk failure. So Reed-Solomon encoding is erasure coding. And basically the description of erasure coding is, let's say you have some file or some object or some blob, and you want to be able to save it in such a way where you can lose a bunch of chunks of it, and you don't know which chunks, but you know that you want a certain amount, you want to keep a certain percentage of those chunks and still be able to recover the whole file. So if you take the file and you break it up in this example into 3 different chunks, because files are just bits, you can treat them as numbers, and sort of, what's the word for when you think about it? Theoretically, you can just sort of treat this as a polynomial of degree 3 out of those 3 data points. So if you just make 3-degree polynomial, 3 data points, and those 3 data points are your chunks of file, what you can then do is oversample the polynomial. So I don't know if you guys are familiar with this hopefully from math, from high school or whatever. You can oversample and then do a Taylor series expansion of the polynomial. So what you can do is lose, I think I have 7 points up there. You can lose any 4 points. It doesn't matter. Any 4 of those points can be gone. And as long as you still have 3 points, you can reconstruct the polynomial and then reconstruct the original data points. This scenario, so the way that this is actually implemented is with Galois and a bunch of other numerical math, so it's not actually fitting polynomials, but this is Reed-Solomon encoding. And so this is what CDs do. This is actually what streams to satellites do to recover from errors. This is what SpaceMonkey does to be able to recover data from distributed nodes. Anyway, useful way of dealing with not having to do triplication or something. So consistent hashing is, this is where you have a bunch of systems, and maybe they're each responsible for storing some object, and that object is, like maybe you have like 50,000 objects and you have 4 servers and you want to add a 5th one, and the way that you've partitioned the data, those are like, you know, you've hashed the server name and then it goes into this thing, and now you add a new server and oh crap, they're all going to go to new servers now. So consistent hashing is, this is actually something that a few different systems use, like so Kademlia, okay. Maybe I'll come back to this. But basically the idea is, if you Google for consistent hashing, you will see a list of strategies for dealing with how to make it so that you don't have to move all of your data if you add a new server to some pod. Okay, so I mentioned Merkel trees. So Merkel trees are basically a way of dealing with establishing some order to a system. So if you've used Git is just a large Merkel tree. The Bitcoin blockchain is a large Merkel tree. And what that means is every object is identified by a hash of its contents. And what that means is if another object references that object's ID definitely cryptographically guarantees that it also references this entire other tree. So this way you can have a large tree of objects and you can compare them exactly by just comparing their IDs. So with Git, a commit ref has inside of it the hash of its file tree, the hash of its parent, and what that means is the ID of that commit ref tells you everything about the entire history of the entire repo files in it because of the tree. So you can use trees in lots of other ways to sort of establish partial order on things. It's very, this is what Bitcoin, the blockchain, does. Boy, I'm going to skip ahead to some of the other things here. I do want to talk about CRTs. So, okay, so I'm going to do this. Okay, so there's a few ways of dealing with consistency between systems that are trying to come to an agreement. And what you do is, Sandra, you just do last writer wins. Just whoever just talked to me last gets the win. That's the value that we're going to go with. You could try and actually do something more complicated like conflict resolution. And what you can do is each make it, you can have a counter, and then if 2 things occur, the later counter. That are a little bit more expanded in the sense that each host has its own counter, and then you take the sort of the global vector maximum for the value. But CRDTs are sort of the most new interesting thing. And basically a CRDT is so this is a convergent replicated data type. And basically if you're building a system that has to agree between a bunch of different processes, a CRDT, what that's going to do is it's going to give you a structure for being able to not worry about consensus. If any edits happen and they follow these properties, you can merge them together. So if you have a CRDT structure, merging is totally safe to do. There's no risk of any problem merging your structure up. So if there's a partition, if there's sort of a split brain syndrome or something like that, they can come together later and it'll be fixed. So if you have a data structure that you're trying to manipulate through a bunch of different systems across different areas of your product, and your operations are associative, commutative, and idempotent, a CRDT has proved that will actually merge up to a valid value at the end. So this is sort of, if you do have a list of operations that follow these properties, this is a great shortcut. You can avoid all sorts of complicated consensus stuff. So, okay.
An example of something that's that.
Addition. Yeah.
Like a counter.
It's not in the
Oh yeah, you're right. Oh, I used the wrong.
Zeros.
Addition of zeros. Do I have a good? Okay, you put me on the spot.
Extra set. Just a set, adding an item into a set.
You're right. There you go.
Set addition.
Set addition. Yep. Yep. Okay. Huh? Yeah.
Boolean.
Okay. So first a little bit of history about Paxos. So about who's heard of Paxos? I'm hoping to convince you to not worry about Paxos ever again. You should go read the paper. Okay. But you have people in the world who understand it. Okay, so in the 1970s, so Jim Gray was a Microsoft research guy. I think he's the guy. So he proposed two-phase commit, and basically this you say I'm about to this value. This is sort of how to deal with consensus. He's trying to come up with a way of multiple machines to agree on a value. So they instead of just saying, hey, this value that because one he says I'm about to do the value, like starts to do a transaction. I'm going to do a value, and like if for then you can have a differing view of what the value is between multiple servers. So they're like, hey, guess what? We can fix this with another phase. So they do three-phase commit, and that doesn't work too well because they just tacked on a thing. So in the 90s, Leslie Lamport is another researcher, and he's trying to figure out, okay, this is impossible. This is totally a nightmare. No one's going to be able to do this. So he starts setting down to prove that distributed consensus is just totally impossible. And in the course of his proof, he comes up with Paxos. And so, okay, so this guy, there's some fun stories about this guy. So what happens is he actually is the originator of the Byzantine general name, and he really loved the Byzantine general name because the Byzantine Empire is known for a lot of infighting and like generals defecting and stuff like that. And so he was really proud of how that analogy worked within the system. So
I think he actually did some research in Greece too, like an article.
Oh, sure, yeah, okay, right. So Paxos, like, basically he writes this paper.
He created LaTeX, just.
No, that's.
Yeah,
Oh yeah. Okay.
You did me really worried there.
I was like, well, oh yeah, okay. So anyway, so Lamport tries to prove that it's impossible, and he ends up actually coming up with a system through his proof that's possible. It'll like work. And so he's like totally like high off of this Byzantine general thing, and he's like, I'm going to write this entire paper with all these references to Greece. And so Paxos, he writes this paper, the Parttime Parliament, and it's about all these Greek senators, and they're trying to come to a consensus. And the reviewers of the paper were like, take out all this Greece stuff, just like take it back. And he was like, no. And so it went into a filing cabinet for like a few years. And actually by word of mouth, people started hearing like Lamport actually figured out consensus. And so people started clamoring, just publish the paper. The Parttime Parliament got out, but for the most part, all the reviewers were like, dude, you gotta stop with the Greece stuff. Anyway, so...
How did the Greek reviewers react?
Oh, I'm sure I don't know. Yeah. But anyway, so he talked this system that he came up with by trying to prove it was impossible. Okay. So he comes up with this and everyone's like thrilled. So then the next paper is, after 3 years, trying to understand the paper, he like, I'm going to write a new paper. Lamport writes, Paxos simple. 2007, some Google engineers, after trying to implement Paxos, are like, no, it's not simple. So that paper came. This paper came out. Oh, did I spell practical wrong? This one came out. I think this is a Microsoft paper. Anyway, so this is actually wrong. This is 2013. Raft came out, and the title of the Raft paper is "In Search of an Understandable Consensus Algorithm." And basically, there's all these like luminaries in the distributed computing research field that don't understand Paxos and will tell you that because it's ridiculous. So in 2013, I think his name is Diego. And Osterhout.
Yeah. Tickle guy.
What?
The tickle guy.
Yeah. Yeah, the tickle guy. I didn't put that together. Anyway, so they come up with they're like, okay, we want to be able to actually make all of the properties that Paxos provides, have the performance that Paxos has, and be understandable. So that was like one of their main goals, was be understandable. And so So the Raft paper was published, I think, late last year, and I gave a talk on this in September. And when I checked, he has a GitHub page up of implementations of Raft. And when I checked then, there was 49. In a month, now there's 54. There's 1 or 2 implementations of Paxos still. And I think Google has one. And they're just nightmares. But Raft is, wow, it's really easy to understand. So I think I'm going to actually switch to a little demo of Raft here. Here it is. Yeah. So this guy is so thrilled with himself that he made a system that's understandable. Let's see, okay. So each server starts up, and what happens is there's basically, Raft has been broken into sort of 3 different components. Raft has a collection within the servers. One of the servers so Raft proceeds to terms. And each term is basically charged. Every term there. Oh, I guess I'm not doing anything. Or server 1 is the leader. And what server 1 is doing is it's sending out heartbeat notifications. Good about random timeouts. These timeouts are all different for each heartbeat interval. And what's happening is when a server hits that timeout, so I think we can actually just shut off this server here. Let's just stop the leader. So they're going to stop getting heartbeats. Is it? Oh. And what's going to happen is one of them is, whichever one, is going to propose to be the next leader. And so then it goes through this leader election process where they vote. And once it has a majority, now it's the leader, and now everything is on a new term. Okay, so basically, now we're on term 3, and server 4 is the leader. So leader election is a big component of Raft. Once you have the leader election thing, basically everything else now is log replication. So when I think with the simulation you put a value or something. I don't know how.
That's one is down.
Yeah, but I think I can still put a value. Oh. Can I put something? I don't know how to use the simulation. Good question.
Yeah, Raft.
Yeah, well. Go ahead.
Raft assume that everybody is cooperating, that we don't have...
Yes. Raft is assuming that there's no rogue or malicious servers. Yeah, so that's a big sort of... Well, but that didn't work with Paxos very well either. But anyway, as far as working in a Byzantine environment, Raft just assumes that everyone is playing by the rules and will gladly give leadership rights to someone else if they ask for it. Anyway, so what happens here, I'll just talk about this. What happens here is, let's say I'm a client and I talk to this server. What'll happen is I'll propose some value, and then before I hear back, what's going to happen is this guy is going to add an uncommitted value to its log, and then it's going to talk to all the other guys and say, hey, I'm going to add this value to the log, and then they reply with the value, or saying that yes, we agree, and once this guy has a majority, it gets committed. And so the majority aspect makes it so that it deals with partition tolerance and stuff like that. And so then it's committed for term 3. Yeah. Let's see. I think this might be a better visualization. But then I have to click through it. Oh, this is the worst. I'm going to let you guys do this later. There's some really great visualizations of Raft online. So because it's actually really great and easy to understand. So 4 implementations of Raft available. So if you want to build a system distributed consensus, you can use Raft. Again, it's as was pointed out, it's not. It doesn't work in an untrusted environment very well.
How does it work if you have very easy drastic partitioning? We have 5 servers in North America and 5 over in Europe, and all of a sudden 2 transatlantic cable time partition.
So number in that scenario, but what it's going to do is it's going to round up. So neither, in that case where you have an even number on both sides, neither one of them will be able to proceed with any more edits until the link is healed. If one of them had more servers, if the majority was on one side of the Atlantic, then the side with the majority would be able to continue making edits, but the other side would not be able to. It would actually just not be able to make any more changes to the system.
The number, not in the sense of you have to have 246 is forbidden. It's even in the sense of the two constants have the same number.
Right. Yeah. Does that make sense?
And is it committing version numbers? So once the link's back up, we take the latest version wins?
Yeah.
Okay.
Yeah.
How well does it scale?
How well does it scale? That's a good question. I think so. I talked to the Salt Stack people had a meetup a few months ago, and they had the CoreOS team by. And I don't know if you guys know about CoreOS, but CoreOS is like a server Linux distribution company, and they actually have a significant amount of experience both developing and working with Raft, because their product etcd is one of the leading Go implementations of Raft. And so they said that they do well up to about 1,000 servers, and they're working on adding sort of a non-participant observer mode so that you can have much more servers still be able to participate by picking someone that it's watching. But yeah, there. I mean, with all the heart, like going back to the wherever it went. Oh shoot. Anyway, there's all these messages going back and forth. Every time you make an edit, there's a proposal and then an acceptance and then an announcement that the value went through. There's all the heartbeats. The more nodes you have, the more of that you have. But okay. Oops. Oh, that's not how you go. Okay. Okay. So those are sort of some useful tools that you can have in your belt, but. Really, the main thing that I think is the main lesson learned is you want to be able to collect data on your system. And collect data on your system, like without having data about how your system is doing, you're flying blind. And that situation, things started falling over at about, I would falling over if I didn't have kind of about the replication logs, what the nodes were doing, like all those sorts of things. You want just a ton of data.
Which services could you use or what are your favorites? Like?
Well, at Mosey it was Graphite, but yeah, I'll get to some things there. Yeah. Okay. So so everyone sort of starts with logging, and logging find way of aggregating all this information. Like if you're just logging, and the other thing that's fun is the places that you tend to do the most logging are the places of code where you've sort of thought about it the most. And the places that tend to have the bugs aren't the places that you've thought about it the most. And so sometimes the places where there's just massive failure going on have no logging. Or maybe there's some logging, but it's totally extraneous and you don't even care about it. So like what'll end up happening is like someone's put a log line in some tight loop, and now your log file is just full of crap. And it's just, the actual log message that you want is one line from like some gzip file way back when. Log lines, if they're not actionable by someone besides you, like which is hardly ever, it's just not going to work. Like logs are, when you get to the point where you have, thousands of systems, the chances of your logs being useful at an aggregate scale for making general decisions as opposed to trying to go back and debug a specific case is very minimal. So sort of to deal with that, having something that you can actually aggregate better makes much more sense. So metrics, when we talk about metrics, typically people mean Graphite here, or at least I do. Graphite is a tool for doing log or time scale analysis of some sort of value. So this is something that I pulled out of Space Monkey Graphite. I think we have some little directory service. And this is, recent ping times. What does that mean? Okay, well, I'm failing at making sense of my data. Anyway, this is an example of a time series graph that you pull from Graphite. And what you have is you plot values that you've pulled out of your system, and you can do sort of math on them, like this has a moving average applied to it of the entire what's happened. And so it's really nice to be able to go back and say, oh, overall, over the last, few months, it looks like, wow, during the weekend we had here, or, I don't know. Being able to have this kind of is much more in logging. The most recent lesson we've learned about this is you want to sample it. And the reason why is because once you get 560 UDP packets of metric data that's gzipped every 2 minutes. And that's, I don't even remember the number, it's a million cloud system is. Sampling is great. You want to sample and not collect everything. You want to be able to sort of back off and actually make sure you have useful metrics, and you don't want to, anyway, okay. A sort of a new avenue to this approach. Oh yeah, go ahead.
Do you have any comments or thoughts on Graphite versus RRD?
Not really. RRD is fine. Yeah, I mean, like basically whatever you can get to scale and answer your queries is wonderful. Graphite, for the most part, has been pretty good to us, but sometimes it hasn't been. So I don't really care. I'd love to see a better tool. So I mean, RRD, we used a little bit of Mosey. I think we switched to Graphite, but this is like an itch that needs to be scratched if someone wants to do a startup, which would not be profitable or make any sense.
Sumo Logic is a tool kind of like that, where you ship your logs out to it.
Yeah, and I guess there's like a stat hat company that's
like
doing.
Keep on it, but it actually works.
Yeah. Okay.
There was a startup called InfluxDB.
Oh, okay.
And I don't think they're making money yet, but yeah, that's what they're doing.
Time series.
Yeah.
Okay.
Replacing Graphite.
Yeah. Okay. Sort of a new approach to this, and this is something that Google started doing, but I don't have any screenshots of what Google does. Actually, I think I found one, but I forgot to put it in this. Google came out with a paper recently called Dapper, and Dapper is a system that they initially started building, and they talk about how they built it, and it ended up serving a different purpose than what they thought it would. And it wasn't really clear to me, maybe because I have horrible reading comprehension, if they talked about what it was initially built for. But this product, what they do is internally, all of their RPC calls and all of their systems internally keep track of tracing information. And so what will happen is whenever a user interacts with the system, each one of these different hops through their system is instrumented in the sense that if it isn't already part of a trace, it'll randomly pick if that trace is going to be sampled. And once it is, it'll keep track of this trace throughout their system. So it'll keep track of what we call span. One of these is a span. And so as it goes through the system, it'll keep track of this span started, and then it stopped. And this span started, and then it stopped. And so you go through them, and it makes all... working on a Go library for Zipkin, which is Twitter's open source implementation of Google Dapper. And so this is an example of it's going to ask a rand host for a random number. As I make the request to the UI host, and then it starts serving the HTTP request, and then I put in some sleep. There's also how it ended up looking in the UI. But this sleep, and then it'll ask for a random message. The random message function will ask for a random number first after sleeping, and then it'll generate a random number and return it, and then once it's gotten it back, it'll actually go and try and get a random message. Anyway, this is totally a contrived example, but so Zipkin is an open source implementation of this Dapper project, but this is really, for the most part, what we end up using Graphite for, is trying to understand a trace through the system. And so I think there's really cool products on the way, such as Zipkin, for trying to understand what your system is doing and being able to understand, okay, this call kicked off 40 parallel requests, and this call is now doing this thing, but what we're really bottlenecked on is this stupid SSL handshake. That's actually really useful information, because then you can actually stop, like, instead of scratching your head with a distributed system and saying, I think our bottleneck is this thing and spending a month on it, you can actually not do that, which I've done, and actually work on what the real bottleneck is. So being able to have data about your system is really useful as far as, moving forward. Anyway. Okay, so that's sort of the end of what I have, but did anyone want to sort of hear anything more about anything, or have any comments or anything before I wrap up? No?
Where's your reading group gonna be?
So that'll be at the Vivint Innovation Center in Lehigh. Yeah.
Any special considerations for embedded distributed systems? Be they distributed across different points on the same car, or distributed between the injector number 5 on the car's engine and injector number 5 on every other car by the same manufacturer?
Not really. I mean, it's all sort of the same stuff. I guess the latencies might be different, but yeah.
And you're more CPU limited on an embedded system.
Yeah. Tom knows my pain. Anyway.
Yeah, so on this graph where there, it looks, I see numbers, but is it basically a profile?
These are millis, or maybe actually those are milliseconds.
Of that.
This is just the duration of this request.
Yeah.
So yeah, it is basically. But it goes across multiple systems, which is like, oh, that's the coolest thing that I haven't seen before. Yeah.
Is that somehow sample, or are you recording every single?
So basically, it will pick when a trace starts if that whole trace is going to get sampled, and so either the whole trace will get sampled or not.
Is there a way to like turn on like sampling on across all requests? Like if you
Yes.
Okay.
So you can flip bug mode, and then it'll just. Yeah.
How does that work? Does each of the systems have to have this software on it?
So right. So the Dapper paper makes a really big deal about how since Google has a very homogeneous system, implemented it at some points within the libraries that all the Google engineers use, and that way the Google engineers haven't needed to worry about it. With Twitter, they've implemented it in their RPC system. So again, the Twitter engineers don't really need to worry about it. For us, we actually have everything in sort of one process for the most part, with like tons of different components inside one process, but then they talk to other processes. So we actually do want sub-process granularity. So the Go library I'm writing is trying to make it easy to instrument, but you still have to add lines of code into your code to get this information.
So one more question. You might have covered it in your Venn diagram, but you mentioned gossip-based. How does like etcd compare to some gossip-based like Serve or these other ones? What do you gain? What's the pros and cons of each? Have you looked at those?
I haven't. I don't know what. Yeah, the other ones you mentioned. I'm a noob.
Gossip is primarily used in distributed searches. You don't need it independent like Nutella. That's where
they people HashiCorp, or they have an implementation. Again, it kind of spreads across the system and kind of.
Well, and they also have a Raft implementation too at this point.
Oh, really? Okay.
Yeah, the HashiCorp is like all about their new Raft library that they just wrote.
Okay.
So I think
the gossip one, and I haven't looked at it, but it's interesting.
Mm-hmm. Yeah. Okay. Nothing else? Okay, I'm going to wrap up then, and then we'll see. So I work at, this is my shameless plug, I work at Space Monkey. Space Monkey is now a division of Vivint. We just got acquired, and Vivint is totally stoked about the Space Monkey vision, and they are really laying it on us. So we have a ton of new projects and funding and all sorts of new things that we're interested in doing in the next few months, few years. We've got distributed hash tables, consensus algorithms, Reed Solomon. Oh my gosh, so much monitoring. I think I had a slide or two I was going to add if I hadn't spent more time trying to deal with the SSL version 3 bug that's now going out. So yay, security and cryptographic engineering. So come work with us if you're interested in this stuff. And then at the Vivint building, I'll be doing on the Thursday every odd month. we'll just do a reading group in the absence of other more interesting information to talk about. So
During the day or evening? The group.
6 o'clock, 6:15, I think. And this is all Utah County.
Yeah, they tell me it was
Yeah. Okay. So that's all. I'll try and post these slides somewhere, if in case anyone's reading more. So.